The James Webb Space Telescope is proving to be an incredibly powerful tool that may have just shattered our understanding of the universe. Out in the depths of space, the telescope is living up to its hype, revealing inexplicably bright galaxies, the potential for life on alien planets, and even challenging our standard model of the universe. The most powerful telescope ever built has astonished scientists with its discoveries of multiple structures that shouldn't exist. This is causing a significant upheaval, leading us to realize that we may have to rewrite all the textbooks about the beginning of the universe. Join us as we explore how the shocking discoveries made by James Webb could potentially alter our understanding of the cosmos. To grasp the dilemma, we must start by looking at the Big Bang Theory, our best supported explanation for the origin of the universe. Initially, the Big Bang was a simple concept derived from three key facts integrated into Einstein's general theory of relativity: a universe filled with a uniform distribution of matter and energy cannot remain static, it must either contract or expand. Observational evidence, such as the distances and redshifts of spirals and ellipticals in the sky, supports this expanding universe model. Combining these observations led to the conclusion that the universe, now expanding and becoming less dense, must have been smaller and denser in the past. Georges Lemaitre was the first to synthesize this in 1927, with others like Howard Robertson, Edwin Hubble, and Arthur Walker reaching similar conclusions soon after. Further developments confirmed that the early universe was hotter and denser, predicting a leftover bath of low-energy radiation in all directions and the formation of initial elements before stars could form. These aspects of the Big Bang have been validated, ruling out many alternatives. Today, we know the universe includes dark matter, dark energy, and cosmic inflation, which together describe the initial conditions at the start of the hot Big Bang and the subsequent evolution of the universe. These initial conditions, from the start of the hot Big Bang all the way up through the present day, allow us to make theoretical predictions and perform numerical simulations that tell us what should arise and when in an expanding universe. Despite all the observational evidence supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that our observations are still consistent with this model. With the recent addition of the James Webb Space Telescope to the arsenal of tools astronomers have, new doubts about the Big Bang Theory have surfaced. Webb's early universe observations cannot be explained by current cosmological models. The telescope has gone further than any similar instruments used by NASA before, giving humanity its first high-definition view of the infrared universe. Thanks to Webb's unprecedented capabilities, we are now discovering and characterizing galaxies from the very early stages of cosmic history. Prior to James Webb, we had one confirmed galaxy, GN Z11, at an age of about 400 million years after the Big Bang, and one other galaxy candidate at around 330 million years. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day, more than 2 years after Webb began science operations, and the story has changed dramatically. We now have over 100 galaxy candidates from Webb that take us back to the first 300 million years of the universe, with several already confirmed as ultra-early and ultra-distant. GN Z11 is now only the 11th most distant galaxy known. All 10 of the top 10 most distant objects were discovered and measured with James Webb. However, many of these early galaxies have puzzling properties that are difficult to reconcile with the theoretical picture. They appear very massive, bright, rich in heavy elements, actively forming new stars, and rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling because it challenges our understanding of how gas infalls onto these early galaxies and how star formation feeds back to prevent future gas infall. There's a limit to how fast material can accrete onto these objects, and although certain physical conditions can temporarily overcome that limit, it shouldn't be sustainable over long timescales. When we look at these early galaxies, it seems that something is amiss. Webb's findings have caused a stir in the astronomical world, with some scientists suggesting that they challenge our current view of galaxy evolution or even our understanding of the universe. In addition to large ancient galaxies, Webb has also discovered massive black holes. The first, Sears 1019, had a mass 10 million times that of our Sun and was found just 570 million years after the Big Bang, making it the oldest black hole ever spotted at the time of its discovery in April 2023. Webb then broke its own record earlier this year by discovering an even more distant black hole in the ancient galaxy GN Z11, 13.4 billion light-years away, seen as it was just 400 million years after the Big Bang. This black hole is around 6 million times as massive as the Sun and is feeding on matter from its surrounding galaxy 5 times more rapidly than current theories suggest is sustainable. According to scientists, this discovery could be a giant step forward for black hole science, especially in understanding how supermassive black holes reached such enormous masses in the very early epochs of the universe. The mystery of how these gigantic spacetime ruptures swelled to such staggering scales so early on is ongoing. Astrophysicists are exploring options, including the possibility that black holes formed from the rapid collapse of giant gas clouds. They also haven't ruled out that some black holes may have been seeded by hypothesized primordial black holes, thought to be created moments after, and in some theories even before, the universe began. In another stunning observation, the James Webb Space Telescope has found thousands of Milky Way lookalikes that shouldn't exist, swarming across the early universe. Shaped like warped vinyls and sporting delicate spiral arms, these Milky Way doppelgangers were found more than 10 billion years into the universe's past, during a period when violent galactic mergers were thought to have made such fragile galaxies impossible. Webb's findings revealed that these galaxies are 10 times more common in the early universe than astronomers previously thought. This strange discovery, along with others made by Webb, points to a deepening mystery around how large galaxies, and with them the potential for life, first bloomed in our universe. Webb's ultra-powerful eye has also revealed glimpses of completely new, unexplainable objects. After being trained on the Orion Nebula, Webb found 42 pairs of Jupiter mass binary objects, or jumbos, Jupiter-sized planets drifting through space in pairs, some as far apart from each other as 390 times the distance between Earth and the Sun. The jumbos are too small to be stars but, bafflingly, exist in pairs, making them unlikely to be rogue planets ejected from solar systems. Their discovery has alerted astronomers to a brand new formation mechanism for planets or even failed stars. Webb's deep space observations have caused a stir in the scientific community. It pierced through dust to find an ancient galaxy, known only by a string of numbers and letters, as TECC 71. This galaxy, located at a distance so far from Earth it often slips in and out of the watchful eyes of various telescopes, is seen as it was just 900 million years after the Big Bang. This was a time when the universe was turning on its very first stars, absolute eons before our solar system was born. Though Webb's view of TECC 71 is a hazy speck of light, it holds important lessons for our understanding of the early universe. Elsewhere, Webb has set yet another record by discovering star clusters in the cosmic gems arc that existed just 460 million years after the Big Bang. This marks the first discovery of star clusters in an infant galaxy seen as it was when the 13.8 billion-year-old universe was less than 500 million years old. The cosmic gems arc, initially discovered by the Hubble Space Telescope and officially designated SPT 0615 JD1, is a gravitationally lensed infant galaxy about 13.3 billion light-years from Earth. This means light from this galaxy seen by Webb has been traveling to Earth for around 97% of the universe's lifetime. An international team of astronomers found 5 young, massive star clusters in the cosmic gems arc. These clusters existed during a period of intense star formation and emitted huge amounts of ultraviolet light, which may have triggered one of 2 major phases in the evolution of the universe, the epoch of cosmic reionization. In another remarkable observation, Webb pointed its sights on a star cluster about 1,000 light-years from Earth and discovered some unusual objects, including what is likely the least massive free-floating brown dwarf observed to date. Additionally, Webb spotted a massive, gassy tendril composed of 10 closely packed galaxies stretching over 3 million light-years. According to researchers, this ancient filament of gas and stars, stretching over 3 million light-years, may represent the oldest known thread of the cosmic web. Another addition to the Webb telescope's long list of cosmic distance records is its discovery of the most distant gravitationally lensed object ever seen, an Einstein ring produced by the warping of light from a distant galaxy around a mysteriously dense foreground galaxy. This ring is a mind-bending 21 billion light-years away, which, given the universe's 13.8 billion years of age, means that the light from the galaxy traveled almost twice that distance due to the cosmos's expansion. Besides making for a very pretty picture, distantly lensed light shows like this could help astronomers understand the puzzling nature of dark matter, the unseen substance believed to make up 70% of the universe's matter. While focusing on unlocking the secrets of deep space, the James Webb Space Telescope is also revolutionizing our understanding of our closest cosmic neighbors. With its powerful infrared instruments, sharp spatial resolution, and exquisite sensitivity, Webb is forever changing our view of our celestial backyard. It is helping scientists answer important questions about our solar system, including how it was formed, how it has changed over time, where the chemicals necessary for life on Earth, like water and carbon compounds, came from, and what the icy small bodies in the outer solar system are made of. Webb's extraordinarily sensitive spectroscopic instruments and state-of-the-art imaging capabilities enable the analysis and mapping of solar system objects' atmospheres and surfaces. This is critical for studying planets, dwarf planets, moons, comets, asteroids, and ring systems. However, because Webb cannot point toward the Sun, it cannot observe objects between it and the Sun, such as Mercury, Venus, Earth, or Earth's moon. Despite these challenges, exciting early results prove that it is possible to study planets with Webb. The telescope captured images and spectra of Mars, allowing scientists to study short-term phenomena like dust storms, weather patterns, seasonal changes, and processes that occur at different times during a Martian day. Webb's view of Jupiter includes many fascinating details, such as auroras, hazes, and tiny moons. It also found carbon on the surface of Jupiter's moon Europa, likely originating from its subsurface ocean. In a recent study, astronomers used Webb to find previously unseen structures and activity in Jupiter's atmosphere above the Great Red Spot. These odd features seem to be caused by powerful atmospheric gravity waves. The Great Red Spot, the largest storm in the solar system, is twice as big as Earth and has been raging for at least 300 years, with winds raging at around 430 to 680 km per hour, up to 3.5 times as fast as a tornado on Earth. Despite the storm's age, size, and power, scientists had suspected that the atmosphere of Jupiter above the Great Red Spot wasn't all that interesting. However, new observations from Webb's NIR-SPEC instrument, which observed the massive Scarlet storm in July 2022, showed that this assumption was wrong. Jupiter never ceases to surprise. The telescope also detected a shockingly large water vapor plume spewing from Saturn's moon Enceladus. For the first time, Webb is giving scientists a direct look at how the water gushing from the surface of Enceladus, first detected by the Cassini spacecraft, feeds the entire system of Saturn, including its rings. Using Webb's infrared vision to study the atmosphere of Saturn's moon Titan, the only moon in the solar system with a dense atmosphere, scientists detected clouds and observed airflow. Titan is the only planetary body other than Earth that currently has rivers, lakes, and seas. However, unlike Earth, the liquid on Titan's surface is composed of hydrocarbons, including methane and ethane, not water. The huge mirror and infrared sensitivity of the James Webb Space Telescope make it easier to see small, faint bodies such as Kuiper Belt objects, comets, asteroids, and centaurs. In its first demonstration of this capability, Webb captured the DART impact, NASA's inaugural attempt to move an asteroid in space. Webb enabled another long-sought scientific breakthrough for solar system scientists studying the origins of Earth's abundant water. Using Webb's NIR-SPEC, or near-infrared spectrograph instrument, astronomers confirmed gas, specifically water vapor, around a comet in the main asteroid belt for the first time. This indicates that water ice from the primordial solar system can be preserved in that region. However, the successful detection of water comes with a new puzzle. Unlike other comets, Comet 238P Reid had no detectable carbon dioxide. Scientists also used Webb to capture the shadows of starlight cast by the thin rings of Chariklo, a small icy body more than 2 billion miles beyond the orbit of Saturn. Only 250 kilometers in diameter, Chariklo is the largest of the known Centaur population. Its rings orbit at a distance of about 400 kilometers from its center. Information gathered from these rings will allow astronomers to explore the ring's thickness, the sizes and colors of the ring particles, and more. Scientists hope to gain insight into why this small body even has rings at all and perhaps detect new, fainter rings. Many different kinds of ice exist in the outer solar system, not just the familiar water ice. Other molecules besides water can form ice, such as nitrogen, methane, ammonia, and carbon dioxide. Webb excels in the study of ices in the solar system through the use of spectroscopy. Most often, it provides reflectance spectra, sunlight shining on an object and reflecting back while the surface absorbs particular wavelengths of light. For ices in the outer solar system, it's not just the composition that matters, it's also the shape and structure. Different structures of ice, such as amorphous, crystalline, and irradiated, look different in spectra. The type can tell scientists about the temperature history of the object. In crystalline ice, the molecules are arranged in a highly regular pattern, forming lattices as in typical water ice on Earth. With amorphous ice, the molecules are irregularly grouped in the cold primordial gas between stars and across the universe. Amorphous ice is the most common form. This is why Webb's integral field units are especially important. With a spectrum in every pixel, scientists can map out the surface of an object. One good example is Jupiter's moon Europa. By looking at a map of the carbon dioxide on Europa, we can tell that the carbon originated in the oceans because it is most abundant in a region where the terrain is quite new. Another example of the exquisite quality of Webb spectroscopy is the clear signature of crystalline ice revealed for the first time on Ceres. Ground-based telescopes had hinted at this ice, but Webb saw the crystalline ice signature for the first time. Some of Webb's most intriguing discoveries involve searching for the building blocks of life beyond Earth. This search hinges on the accurate identification of chemical markers such as water, carbon dioxide, and ammonia. These markers have strong infrared signatures that Webb can detect in the atmospheres and on the surfaces of planets, moons, and smaller bodies. In a remarkable finding, James Webb has spotted potential signs of life in the atmosphere of an alien planet, K2-18b, a sub-Neptune planet weighing in somewhere between the mass of Earth and Neptune, orbiting in the habitable zone of a red dwarf star 120 light-years away. After taking an atmospheric spectrum, Webb found it rich with hydrogen, methane, and carbon dioxide, all chemical markers of a hydrogen-rich environment that is a prime contender for extraterrestrial life. More tantalizing still was the detection of dimethyl sulfide, a compound only known to be produced by microscopic algae in Earth's oceans. The researchers want to take more observations of K2-18b to confirm these findings. Fascinatingly, the latest results from the James Webb Space Telescope suggest that the exoplanet LHS 1140b, orbiting a red dwarf star about a fifth the size of the Sun and sitting 48 light-years away from Earth in the constellation Cetus, could be our best bet at finding an alien ocean. LHS 1140b, which resides in its star's habitable zone, the Goldilocks zone, has been of interest to planetary hunters for some time. It had already been theorized as a potential water world, but scientists needed Webb's keen eye to confirm whether it was a mini-Neptune or a super-Earth. Recent data from Webb has strongly excluded the mini-Neptune scenario and suggested that LHS 1140b may have a nitrogen-laced atmosphere, much like Earth. This is a promising start, as Webb's data indicates that the exoplanet's mass might consist of between 10% and 20% liquid water, potentially making it a world with an Earth-like atmosphere and a surface temperature conducive to liquid water. Additionally, Webb's data paints a fantastical picture of LHS 1140b as a planet that might resemble a snowball with one side always facing its star, similar to the Moon's orbit around Earth. This means one side could be exposed to significant heat, melting part of the snowball into a liquid ocean. Such characteristics make LHS 1140b a prime candidate for the search for extraterrestrial life. Webb's capabilities have also allowed scientists to study other fascinating exoplanets, such as WASP-39b, revealing new details about their atmospheres and weather patterns. Beyond exoplanetary research, Webb has provided insights into our own solar system's formation, the tumultuous early years of planet-forming systems, and the explosive deaths of massive stars in the early universe. Webb's observations continue to revolutionize our understanding of the cosmos, promising more stunning discoveries and beautiful images in the years to come.